Ave Coders. Simple linear regression is when we have a single explanatory variable, or in other words, we have one independent variable and one dependent variable. By convention, these are our x and y, and essentially our task is to find a linear function that is a non-vertical straight line that can as accurately as possible predict the dependent variable values as a function of the independent variable. And it is called simple because our outcome variable is related to a single predictor. Alright, how do we know how to draw that line? Well, although we can sort of guess from the picture what would be the best way to draw it, it is no good for a computer because it needs some sort of mathematical explanation. Therefore, we need a formula. This is a formula of the regression line where y is the predicted value of the dependent variable for any given value of the independent variable x. Alpha is the intercept, in other words, it is the predicted value of y when x is 0, and beta is the coefficient or the slope that explains how much we expect y to change as x increases. Sometimes there is also an error added to that formula explaining how much variation there is in our estimate of the regression coefficient beta, but we'll keep things simple this time and we will exclude it. Also, some formulas use a different notation, and instead of alpha and beta, they use beta 0 and beta 1 respectively, so don't fret. These are the same formulas, just with different notations being used. And the main job of this simple linear regression model is to find the best fit line through our data by searching for the regression coefficient, or beta. Also, our simple linear regression example would be based on a few assumptions. First, we assume data's homoscedasticity, or homogeneity of variance. In simple words, this means that the size of the error in our prediction doesn't change significantly across the values of the independent variable. The second assumption is that the observations we are working with are independent, meaning that they were collected using statistically valid sampling methods and there are no hidden relationships among these observations. And the third and final assumption is that the data follows a normal distribution. But enough theory, let's get to the code. First of all, I'll leave the link to this Google Colab in the video's description, and we begin by importing the libraries that we will require. First of all, we need to specify that we want our plot to be shown below the cell that generates it. Therefore, we call matplotlib inline, otherwise it will be in a pop-up window. And now we will import the matplotlib library pyplot as plt. The next library is of course numpy, because we're going to be dealing with arrays. In particular, we're going to be generating some synthetic data, and pandas as pd, and of course sklearn, from which we'll import this linear regression model. In fact, here we can write from sklearn and then dot linear model, we import linear regression. So this is our simple linear regression model. And also from sklearn dot preprocessing, we'll import the scale. This is to standardize a dataset along any axis. Also from pylab, we'll import RC params. This is to define a runtime configuration that it will contain the default styles for every plot element that we create with matplotlib. But essentially, all we'll define with it at the moment will be the size of our plot. So down below, we can write RC params, and then inside the single quotes, figure.figsize, and then we'll specify 10 by 8 inches. I can't remember whether it adjusts to your locale, so whether it's going to be not inches but centimeters or whatever use where you are at the moment, but 10 by 8 is pretty reasonable size. So the problem we will be solving with this simple linear regression is pretty straightforward. So there will be a direct linear relationship between the variables. And you might be asking yourself, why am I showing this building? Well, strolling around some of the historical towns, in particular in Europe, you can notice that some buildings have space for a window, but they don't have a window. And the reason for that is the so-called window tax. So there is a basic linear relationship between how much tax you pay that is dependent on how many windows your house has or had, because this tax is a thing no more, thankfully. And now they're looking to introduce the bedroom tax, but this is a totally different story. So the data for this problem will be completely synthetic, or otherwise it will be completely made up. So we're going to generate this data ourselves just to show the principles. So first we need to generate our axis. In our case, this is going to be windows. Windows will be an array that will hold randomly generated numbers that will represent the numbers of windows per house. So imagine that in our area, houses have from 10 to 50 windows each, and we are looking at 100 of these houses. So let's have a look at that array. Oops, I think I forgot a comma. So there should be a comma after 50. So this is the windows array, which represents how many windows each house has. And also this is going to be our x. Next, we need to define our y's, and this is going to be pretty straightforward as well. This is going to be our tax. So the more windows you have, let's say we have £256 for some administrative fee, and then we charge, let's say, £100 for every window. Let's print them out, and this should be another array of values, pretty straightforward, quite a big tax, I should say. And to help us to visualize this linear relationship between our two variables, our windows and tax, it is a good idea to plot them. So it's not going to be a sophisticated plot. So we just throw these two variables into the plot function from pyplot. So windows and tax, x and y. And then we also specify the type of the pointer. So if we're not going to specify, it's going to be like a round dot, but we want triangles pointing upwards. And also on the x-axis, we need to specify the label, and it's going to be, we'll just say windows. You can write something else, more descriptive if you want. And in a similar fashion, y label will represent the tax. Now, of course, we need to give it a command to plot. So plt.show. Let's run the cell. And as you can see, there is a simple linear relationship between our windows and the taxes we pay for the amount of windows we have in our houses. You can enlarge this plot if you want to, just to clarify it is indeed linear relationship. We can also add some random values to our task variable, but the idea, the principle will remain the same. So we can add some random number to our tags, and if we look at the plot, it's going to be pretty much the same. And if later on at some point I'll decide to swap this plus to minus, so subtract this random value, then basically the plot will also remain the same. So the relationship between the x and the y's will still be linear regardless. So let's make sure we rerun that cell. We did. So if I'll rerun the cell that generates the plot, we'll see that the picture will pretty much remain the same. And now when we can visualize this relationship, we can get on with the linear regression model. But first of all, rather than operating with windows and tags, we can convert them into X and Y. So X is capital and Y is not. This is a convention. And down below, we can define our linear regression model. I'll call it linreg, and this linear regression model is what we imported from the sklearn. And after we've instantiated this linear regression object, it's time to fit the model to the data. And as you remember from the formula, we have intercept and we have a coefficient, which is the same thing as the slope of the line. Therefore, we can now print these attributes of our model, which is intercept and coefficient. So linreg.intercept underscore and linreg.coef underscore. The value returned by the intercept illustrates that our model predicts this response when x is 0, and the value returned by the coefficient or slope means that this predicted by the intercept response will rise by the value of this coefficient when x is increased by 1. And finally, we can check whether the model works good or not by obtaining the so-called coefficient of determination, or r squared. And we can do that with the score function called on our model. So basically we determine how our model performed by assessing this score and how close it is to 1. And here you can see it is very close. And once we are satisfied with model's performance, we can actually use it for predictions with either existing or new data. But because the new data will be pretty much similar to the one we've used already, and because this is a simple linear regression, I expect nothing but the highest possible scores in our predictions. But let's have a look. Let's create a new batch of our synthetic data. So on the new line, the new cell, I'm going to declare a variable, let's call it new windows. Or you know what, let's convert them to x and y straight away. So let it be not new windows, but something like x new. All right, and this variable will store this array of numbers that will be, let's say, from 5 till 10. This is going to be our range, and this will represent number of windows in the houses, in 100 houses. So these are the first 10 records. Let's actually make it from 3 to 10. I'll be much more logically correct and will give us more sort of values to work with. And we also need to define our y's, so our tags. But this time we'll not be formally calculating the tags, we will be predicting the tags. So on our model linreg, so linear regression model, we will call a function that's called predict. As an argument, this predict function will take our new x's, so x new, and it will predict our y's, y new. So let's print x should be capital. Let's print our y new. Here are our y's, our tags predicted, and let's plot these values. I'm pretty sure the plot will pretty much resemble the one we already have. So we just need to replace windows with x new and tags with y new. And once we've done this, let's also Well, let's leave the labels. So here is the plot. Everything is pretty much straight as it is expected. Let's print the scores as well. That should be like close to 1, I would reckon. Let's do it in the new cell. And let's run the score. And here we go. This is our alt score. We need to change this to X new and Y new. Let's run it. And as you see, it's literally 1. Usually we say that the absolute score is not something that can be trusted, but this is an example of a simple linear regression. Plus, we're not adding the error term. I was basically showing the main principles, how linear regression, the simple one, works. There are more examples of linear regressions, such as multiple linear regression and polynomial regression, that are much more interesting and, of course, much more enjoyable. But you can try this simple one on another set of synthetic data, or you can possibly download a simple data set that was constructed just for this simple linear regression. But I would say that more adventures are coming our way. So please give this video emperor's thumbs up, toll the bell, subscribe to the channel, and I'll see you in the next lesson. That was V. Thank you and goodbye.